Hey everyone, we are NASA's interns with the Galaxy Classification Team 2024, and today we'll be giving a presentation on dark energy and the expansion of the universe. I'm Lino Marrero, and I'm from Frisco, Texas.
I'm Praharshini Nernuru, and I'm from Round Texas.
I'm Annie Vo, and I'm from Sacramento, California.
I'm Johanna Greer, and I'm from Memphis, Tennessee.
So our team researched dark energy. But what is that? We really don't know. It was discovered in 1998, but previous research has been done for a few decades before. The idea began to take place in the 1920s when Henrietta Swan Leavitt discovered that Cepheid stars, which are a type of variable stars, their brightness fluctuated based on distance. Combining this discovery with other research, such as the redshift discovery, led to the belief that there is some force responsible for the expansion of the universe. However, a key idea to note is that dark energy should not be confused with dark matter. Dark energy is a repulsive force, while dark matter is an attractive force. To understand dark energy, one must understand the various models of the universe. There are four main types of the universe timelines. The recollapsing universe theory shows that the universe will start with a big bang and end with a big crunch. The critical timeline theory shows that the universe will become stagnant after a given point. The coasting theory shows the universe growing in a linear fashion, and the accelerating theory shows the universe growing in an exponential rate. These theories are directly affected by dark energy. The decelerating universe theories, which are the first two theories given, these do not consider dark energy since there is no universe expansion. However, the other theories do include dark energy as part of their models since it shows that the universe is growing. Scientists recently came to the conclusion that our universe is accelerating in an exponential rate. But how do they do this? One of the main pieces of evidence given for an accelerating timeline is the supernova theory. Type 1a supernova have a constant brightness, which can be measured to calculate distance. However, when scientists tried to calculate distance using another method, using the redshift method, they noticed that the distances that they calculated were not the same. Astronomers believe that this irregularity is due to dark energy. This brings us to a research question. Can we find evidence to indicate the existence of dark energy?
All right, so let's start off with a little bit of galaxy vocab. So first of all, we have redshift, which you guys have already heard. Redshift is the amount of a galaxy's light that is stretched towards the red end of the spectrum, and it's due to the expansion of the universe. And essentially, we just use it to measure how fast the galaxy is moving away from us. Next off, we have right ascension, RA, and declination, DEC. And like Earth's surface coordinates, but only for objects in the sky, like stars and galaxies. RA is like longitude, measuring east to west position in the sky along the celestial equator, and DEC is like latitude, measuring from north to south position in the sky relative to the celestial equator. Finally, the last vocab word we have is confidence level. It's rated on a scale from 0 to 1, and it shows us how confident the HECDEX data analyzers are that a galaxy is truly a galaxy and not noise. So the closer to 1, the more likely it's a galaxy.
So we discussed right ascension and declination a lot throughout our project. So we decided that it's a good idea to have a visual representation. So as you can see, the declination and right ascension are used to indicate where an object is relative to the celestial poles. The sphere that is seen surrounding the Earth is the celestial sphere.
Next, we gather information from the HEDEX. The HEDEX is the Hobby Eberly Telescope Dark Energy Experiment at McDonald Observatory. It uses a set of spectrographs to map the three-dimensional positions over 1,000,000 galaxies. It also aims to create the largest map of the early universe. That map is able to tell us the rate at which the universe expands at specific points in history, and that highlights the place dark energy has in the history of the universe and its influence on objects. We also use Dark Energy Explorers, which is a citizen science project utilizing data from the HEDEX telescope. We use volunteer input to distinguish classifications between galaxies, black noise, or black holes, and noise. The objects are 9 to 11 billion light years away, and it helps us to extend our understanding about dark energy and its contribution to the expansion of the universe.
When classifying our data, there were 4 different types of data that we looked at. First, we looked at fiber images. Each of the colored boxes seen on the left shows one type of fiber image. Then we looked at spectrographs. which can be used to find redshift and distance. We then looked at imaging postage stamps, which show the location of atoms of the given data. Lastly, we looked at line flux maps, which show the absorption and emission lines, which can be used to find a lot of data, including temperature and density of the objects that we were looking at.
All right, and now into our hypothesis, which is that we can use HETDEX data to find galaxy clusters in the early universe at 9 to 11 billion light years away.
But for a galaxy to classify as a real source, we need to look at data. So for our first set of data collection, we look at spectrographs. So these blue dots are actual data points and their ranges, and the spikes are their emission lines. And when they lines up with the black line there, then that means it's good data, and that means it's an indication of no noise and no skyline. And it's a good line of fit because it has to be on the black line. Another thing about these spectrographs is that black holes can be identified easily as they have a longer wavelength and they're easier to distinguish. But moving on, if the plots and the dots fit, then we will analyze the line flux map. So on the left, we have a bright yellow dot in that red square, which is a good indication that that's a good signal. And on the right, we have no distinction between anything, which means that is just a sea of noise and it can just be classified that way and thrown out. And then we move on to talking about the fiber images. In these images with the colored borders, we see a distinct black dots on the left side in each image that help indicate a galaxy. And that will help distinguish between a galaxy and just noise. So the gray is noise and the black is signal. Each signal is a composition of several spectra, and the rectangle show individual fiber spectra. The black box is a combination of all colored boxes, and as a result, if we see a strong signal in each of the colored boxes, then we can more confidently say that it's a galaxy. If it's only in one box, then that means it's just noise. Streaks also indicate bad data and should be thrown out. With this data, we can also identify black holes. So you can see that it's not a galaxy and it's not noise, but it's a black hole. Those are very rare, but it's also not important to the Zooniverse project as we're looking for galaxies.
So why clusters? What makes them significant and why are they important to us? Well, dark energy is the theoretical idea that if it exists, causes the universe to expand at an accelerating rate. If a cluster is found, then the belief that dark energy exists can, if we analyze the way clusters and the galaxies looked then versus how they do now, we can see if they spread apart, which would then mean that an outside force had to have pushed them away from each other. That outside force could be dark energy, since if we find the galaxy spread out, it can indicate the universe is expanding at an accelerating rate, which is done effectively by a dark energy. But our goal is to plot out the locations of galaxies so we can find the clumping of galaxies indicating galaxy clusters. These galaxies are from the earlier years of the universe, existing anywhere from 9 billion to 11 billion light years away. Analyzing our data sets. We looked at more than 130,000 classified galaxies from the public data release of HETDEX through the Dark Energy Explorer Citizen Project. The first steps we took to manage this much data was to narrow our declination angle range to anywhere between 49 and 54 degrees and limit any results we got to a confidence level of 0.75 to make sure we were being accurate and reliable.
Okay, and now we're going to go about our cluster collection. After narrowing down our data sets, we are ready to start identifying clusters by eye. We visualize the data in a 2D Cartesian coordinate plane by dividing the galaxies by small declination ranges and use the redshift cosine right ascension and redshift sine right ascension equations to determine the x and y coordinates for each galaxy and plot them on graphs. This allowed us to determine if there were identical galaxy clusters by eye. So right here, we have one example of declination range 49 to 50. And in the red box, you can kind of see some concentrated clumping of galaxies. So we decided to check it out. And after we identified potential clusters, we had to narrow down the graph for the selected points and replot our points on a DEC versus RA graph and check the distance to ensure they're actually close enough to be a galaxy. So while on the bigger graph in the top right, you can see that it does look like they're clumped together. On the lower graph in the bottom left, DEC versus RA, you can actually see the points are pretty spread out, which is a strong indication that this is not a cluster. However, we were able to locate two more potential clusters based on clumping by eye in the declination range of 53 to 54, labeled below 1 and 2. And in our first one, after we narrowed down the data, or narrowed down the graph to a smaller DEC versus RA range and plotted it on the graph you can see in the bottom left, we can see that they're actually packed pretty closely together. And this is likely a cluster candidate with around 16 galaxies. And again, on the top right, you can see where our original clumping was. And this was potential galaxy cluster number 2. And again, in the top right, we looked again and good indication of clumping. We go down, look at the DEC versus RA graph, and yes, it definitely looks like it could be a cluster candidate with 12 galaxies.
So what are the results? We learned to classify galaxies. We helped sort data for the next release. We used previous classified galaxies to discover clusters in the early universe. We found that new clusters were 10.5 gigalight years away, and this all helped us to better understand the universe's expansion.
How can we sum up our NASA's experience? We all had an amazing time, and it's very hard to sum it up into short sentences, but we tried. For me, it was a great opportunity to learn a lot, meet tons of great people that I will be friends with for life.
For me, NASA's internship has been an amazing opportunity to meet new people, try new things, and learn a ton.
Personally, this program allowed for a lot of growth and personal connections to grow, all while discovering new things.
This NASA internship was an amazing opportunity, and I felt like it opened the door for many more opportunities in the future. I met some amazing people and I learned a lot of great things, and I'm so excited to be part of this trip.
Okay, and here's our references. And yeah, thank you guys so much for tuning in. And also, we'd like to say an additional thank you from all of us at the Galaxy classification team to NASA, NASA C, CSR, Dr. Judit Ries, our mentor. Thank you very much. And additionally, Miss Margaret Baggio, Miss Tomlin, and Miss Selena Miller. We really appreciate you guys a ton. So thank you so much for this opportunity.
And scene.
Yeah.